Hula. That means hello and welcome in Fiji.
So much.
Welcome. Let's go ahead and get started. We have a lot of ground to cover today. Would someone be willing to give us an opening prayer to get us started on the right foot?
Thank you. I haven't been outside in 2 days.
Thank you. Bye.
Dear kind and gracious Heavenly Father, we're thankful to be here today and that we're able to learn, and we ask to have thy spirit with us, that we can have our minds opened and that we're able to get our work done and perform well in our activities. Father, we love thee so very much, and we're so thankful to be here today, and we say these things in the name of Jesus Christ. Amen.
Okay. I can highly recommend going to Fiji. They're the most friendly, warm people I've ever met. Just so happy, and just everywhere we went, people were just waving to us and smiling, and they didn't even ask us for money. It was quite a refreshing place. Let me talk to you quickly about the exam. When we finished exam A, we had an average of 75.5, and 182 of the class earned an A on that exam. And then we went over the exam via video and took exam B. And after exam B, the average had raised to 85%, right on the cusp between an A and a B. And here's the big news. The number of people that earned an A on that exam went from 182 to 341, 63% of the class. What that tells me is that a whole lot of you went into exam A with a sort of model. You know, you kind of had it figured out. But then before exam B, you nailed it. You finally saw the light. You saw, oh, that's how it fits together. And then you went in and exam B was just a piece of cake. Now, the number of perfect scores went from 39 up to 61. The number of D's went from 51 down to 31. The number of failing grades went down from 65 to 20. Now, here's the message that I would like to leave with you. Many of you use that exam A to motivate you to get ready for exam B. On the final exam, there's not an A and a B. They won't let me do that. During finals, you just have to give one exam. It has to be open the whole week. So there's just an A. And so whatever you were doing to figure it out before exam B, do that before exam A, okay? So you can get ready for the final. Now, turns out that 61% of the class took both exams. I looked carefully, and the reason that's so low is that a lot of us did so well on exam A that we didn't feel a need to take exam B. And that seems reasonable, okay? Now, 86% of the students that did take both exams increased their score, and the average increase was 17.7%. That's huge. That's huge. And so I think that this process of bumping up against the exam and then reevaluating and then taking a second exam has been helpful. Are there questions about the exam? Yeah. The final exam will be on the new material on magnetism that we're covering now. It will not. It will just be the new material that now, having said that, you notice in your homework that when you were working homework with magnetism problems, you also had to still remember, well, what was the electric force like? The electric force was this way. The magnetic force had to be that way. So you still need to know some of the basics, but it won't be covering those ideas. Okay. So let's talk about why magnets are magnets and review what we've learned about magnetic fields and forces. The first thing you know is that magnetic forces are more complicated than electric forces. Electric forces were straightforward. The electric force was either in the same direction as the electric field if it was a proton, or opposite direction if it was electron. Easy peasy. But the magnetic force we find is always, always, always in a direction perpendicular to the direction of the magnetic field. So getting the field and the force separate in our minds, knowing which is really important. And today we're going to work on that. It involves 3 right-hand rules that we covered in this week's tutorial, and I'll be reviewing those. Now, back in the day, many, many years ago, there was a Unabomber, and he was hiding in a little shack in outside of Helena, not far from Bozeman. And then there were these sovereign citizens that were down closer to Butte that were in a compound. It was a crazy place. Everyone had guns. Anyway, that's when this cartoon came out. Never mind. Okay, we found last day that if a moving charge can experience a magnetic field, a moving charge should be able to create a magnetic field. And that just makes sense by Newton's third law. If I can put a normal force on his chin can put a normal force on my hand, okay, by third law. Now, the person that demonstrated this was Hans Christian Ørsted. And I'll remind you, this was one of the few things that ever happened during a lecture that was worthwhile. Okay, you know it in your heart, right? You know it in your heart. He was lecturing. He happened to have a wire with current going through it. It was hooked to a primitive battery, and he had some lodestones. Lodestones were just magnetized rocks that were free to rotate. They were primitive compasses. And so what he had was essentially this setup here. Whoa, back, Greg, back. Didn't mean to do that. Okay. Use all 3 fingers. Okay, so what I've got is a wire going straight down, and it's surrounded by a bunch of compasses. And when I flip the switch, we're going to send current, and that current is going to go up towards the ceiling through that wire. And that's going to set up a magnetic field. And let's look at the direction of that field. Oh, okay. You see how now when this light goes off, the current goes off. This thing, when it gets hot, turns itself off. And so you see that the compasses go back to their original position pointing towards Canada. And then it goes on again, and they make a circle. Much like that. Okay. Now, that's the only possible answer. Remember last semester we talked about using symmetry. Actually, it was this semester when we were talking about electric fields. If the problem has a certain symmetry, the answer has to have the same symmetry. If I've got current going through this wire towards you, the magnetic field caused by that current has to have the same symmetry. Well, if you look at this wire standing on your head, it looks the same. If you tip your head 30 degrees, it looks the same. Tip your head 80 degrees, it looks the same. Any angle. And so that means that the answer has to look the same. And the answer is the magnetic field line. The magnetic field lines are circles that go around this wire. Now, there's 2 ways to go around the wire, but the magnetic field only goes around one of those ways. And I remember which way by using my right hand. And we call that the right hand rule. This is in the way. Let's get rid of that. Sorry. My right hand has a straight part, the thumb, and since the current's going in a straight wire, let's use the thumb to represent that conventional current. I'm always talking conventional current. My right hand has a curved part. We'll use that to represent the magnetic field lines that wrap around that wire. Okay, so if the current's coming towards you, those magnetic field lines are going to wrap around counterclockwise from your point of view. Okay, that makes sense? Now, if we look at this wire here and ask what do the magnetic field lines look like, well, if I look up here, I use that right hand rule. I put my thumb in the direction of the current, and up there, the magnetic field lines are coming out of the board. And I represent that with this arrowhead here, out of the board. And if I look up here, it's still out of the board. If I look down here, well, down here, it would be into the board. That hurts. Okay. And if I look down there, it would be into the board. Now, that doesn't speak to my soul so much. I think it's easier to see with this end view. And at the end view, we're looking at that wire the way we were before, right at the end of it, and the current's coming towards you. And now, if I look up above the wire, okay, now I can use right-hand rule. My thumb is the current, and my fingers are the direction of the B field. It's going to be to your left. Now, here's the part that's new. If I look up there, it's also to the left, but it's weaker. Further away, weaker. That just makes sense, doesn't it? Makes sense. Now, if I look down below, again, by right-hand rule, that's going to be to the right. But if I look further away, it's going to be weaker. And the rule that we can only prove with calculus, and we're not going to go there. You're just going to have to, I hate to have you do this, but you're just going to have to trust Greg. I mean, boy, that's scary. But the rule is twice as far, half as strong. The magnetic field due to a long straight wire falls off as 1 over R, 1 over the distance away from the wire. It's inversely related to the distance. Now, if I look at the magnetic field line, that's the green circle. This is a magnetic field, and that vector only tells me the magnetic field at one point. But remember, the field lines, they paint a picture throughout all the room of what the magnetic field looks like. And if I wanted the magnetic field here, it would be this way. If I wanted the magnetic field here, it'd be straight down. It's tangent to the field line, just like when we were dealing with electric fields. See if your neighbor's on the bus. Do a buddy check.
Yeah. So. I'm like, oh,
My fingers are wrapping in the direction of the
green.
Yeah.
Your fingers. That's wrong. I'm not sure it doesn't take into account
Yeah.
Now this side is like
Right here.
this one, for example. The right one.
Okay.
That's why the arrow.
Now, this is an important problem because it highlights the main tool in your toolbox when dealing with magnetic field problems. It's not about what you care about. It's about what you don't care about. Hear me out, okay? If I want to know the magnetic force exerted on wire 1 due to wire 2, okay? I know everything there is to know about the magnetic field due to both of those wires. By right-hand rule, I know that the magnetic field due to this wire goes in on this side, comes out on that side, wraps around. I know the magnetic field due to this one is the same way. But I don't care. I don't care about the magnetic field by both wires, because both wires aren't pushing on wire one. If I'm looking for the force on wire one, it's only wire two that's pushing on wire one. Wire one's not pushing on itself. So the magnetic field that I care about is the magnetic field created by wire two. It's a two-step dance. First of all, wire two makes a magnetic field, and then that magnetic field pushes on wire one. Well, let's look at the magnetic field due to wire two. Okay, by right-hand rule, it goes into the page over here. It comes out of the screen over here. I know what it's like everywhere. But I don't care. I don't care what it's doing over here. I only care what it's doing over here where it's doing the pushing. Okay? And over there, it's coming out of the screen. Does everyone see why it's coming out of the screen? Okay. Wire two has done its job. It set up this magnetic field at the location of wire one. Now that magnetic field is going to push on wire one. Which right-hand rule from the tutorial tells me what direction the force is going to point? One. That's the only right-hand rule. You've got three of them. We'll review them today. That's the only right-hand rule that gives you the direction of the force, the actual push and pull. Okay? So let's use right-hand rule number one. I reach in the direction of the flow, of the motion, up. I turn my wrist so that I can wave in the direction of the B field. My thumb is pointing in the direction of the force. Does everyone see how I got that? Now, people, in your homework, on your exam, I encourage you to always pick up your paper, pick up your computer, and turn it so that you can reach away from your body, so that you're not doing right-hand rule like this where you're getting all confused. Now, I couldn't do that here because the screen is the screen. But when you're taking a test, that test belongs to you. Pick it up and turn it around so that you can reach away comfortably and turn your wrist. Okay? Now, how do I find the force on wire two? Well, there's two approaches. One approach is to say, I believe in Newton's third law. And Newton's third law always applies. If two is pulling one to the right, then one is pulling two to the left. End of story. Or I could go back and do what I did before over again. If I'm looking for the force on two, the only magnetic field I care about is the one caused by wire one. Now that field due to wire one is going to be into the screen over here, out of the screen over here. But again, I don't care what's going on over here. I only care what's going on over here. Okay? And over here, the magnetic field caused by wire one is into the page. Into the page. Well, now I'm ready to find the force on wire one. I'm sorry, wire two. Wire two. Okay? I reach in the direction of the current. I turn my wrist so that I can wave in the direction of the B field. And sure enough, I get a force that's consistent with Newton's third law. Check that your neighbor just followed that, please.
There you go. You just to begin. Yeah, it was like
This one, quicker, Candace, where you're going.
Spider-Man. The flow's going.
Okay. I have a demonstration of that. I've got these two bars that are, we can think of them as wires, and I'm going to send current up in both of those wires in the same direction. And this is very sensitive. It wants to be on a level surface. When I push the button, the current travels and they come together. Did everyone see them come together? Okay. Physics works. Okay. Now that's what this demo looks like in Montana. We didn't have fancy equipment. We just had two wires that were just hanging there and they would come together. Okay. Now, what if I make one of these currents the opposite direction? Instead of both being up, have one down, turn that arrow around and flip this switch. Well, let's see what happens. Oh, they repel each other. Well, let's figure out why that is. Again, if I want the force on wire 1, I want the magnetic field caused by wire 2 at the location of wire 1. Well, now wire 2 has current going down, conventional current down. And that means by right-hand rule number 2, the field over here is going to be into the screen. Over here, it's going to be out of the screen. It wraps around, in, out, in. But again, I don't care what's going on over here. I only care about what's going on there. And over there, it's into the page, into the screen. Well, now, if I use right-hand rule number 1, I reach in the direction of the flow. I turn my wrist so that I can wave in the direction of the B field, and that gives me a force that's a repulsive force. I can now use Newton's third law and say that 1 is pushing on 2 the other way. Or I can go back and do the whole thing over again. If I want the B field over here caused by wire 1, well, by right-hand rule number 2, that B field wraps into the page over here, comes out of the page over here. But again, I only care about what's going on over here. And over here, it's into the page. So now this is where it gets difficult because I can't turn the screen around. I've got to reach in the direction of the flow and turn my wrist so that I can wave in the direction of the B field, and that gives me a force to your right. Okay, and that's what we saw here, was that they repelled each other. Do another buddy check real quick. Check on your neighbor. Okay. Let me review the 3 right-hand rules that we went through in the tutorial. The only right-hand rule that gives a force, an actual push or a pull, is right-hand rule number 1. And in right-hand rule 1, we first acknowledge that there is no force unless there's motion, unless the particle or the current is flowing. And we reach our hand, our right hand, in the direction of that motion. And then, this is the most important part, we turn our wrist so that we can wave in the direction of the B field, and our thumb is going to give us the direction of the force for a positive charge, like a proton. If it's a negative charge, like an electron, you reverse it. You reverse it. Now, folks, in the Help Center, someone might try to teach you the FBI approach. Yeah, has that happened? Yeah. don't listen to them, okay? Some people swear by that approach, but in this class, you're just going to get confused because I'm going to be doing the reach and wave approach, and you're going to be doing the FBI approach. Just find someone else to help you, okay? Now, this is the type of problem that would involve right-hand rule number 1. And I'm going to tell you right now, this problem's on your exam, your final exam. It's going to be a different velocity, but it's going to be the same magnetic field because it's the magnetic field of the Earth. And I can't change that. Okay? They won't let me. No, the magnetic field of the Earth is towards Canada. And I know Canada's that way, but for the sake of this screen, let's say Canada's this way. And the magnetic field would be towards Canada and down 70 degrees. And in this homework problem, you've got a proton traveling east. Now, if that's north, if that's towards Canada, if you're headed towards Salt Lake, where's the mountains? Yeah, that way. That's east, okay? So it's headed east. And so if I want to find the force on that proton, I use what's called the Lorentz force that we covered last day. This is the charge. We know that's the elementary charge. We're given the speed, that's 5 million meters per second. We know the magnetic field of the Earth is about a half a Gauss, or 5 times 10 to the minus 5 Tesla. And this is the hard part. This is where people fall down. This is where people lose points, is using the wrong angle. Okay? Now, folks, these magnetic problems are inherently three-dimensional. And some of us are really good at seeing problems in 3 dimensions. Some of us are not. Okay? I would encourage you to bring props to the exam. You know, different colored pens that you can point in different directions, kind of, casually, so that they don't throw you out of the testing center. Okay? But what you would do in your dorm room is you would point one hand in the direction of the velocity vector, east, and one hand in the direction of the magnetic field, towards Canada and down 70 degrees. And then you would ask yourself, what's the angle between my arms? What's this angle? Yeah, what's this angle now? 90 degrees. Did I change the angle? No, I did not. So it's 90 degrees. And so what you would plug in is 90 degrees. Now on the homework, some of you put 70 degrees and you got an answer that was oh so close, and you were thinking, oh, I missed points because of round off error. Oh no, the sign of 70 degrees is not that much different from the sign of 90 degrees. You didn't lose the points due to round off error. You lost it due to I don't understand error. Yes.
Is the angle always 90?
It is not. And that's the beautiful thing, is that I can make it different on the exam. For example, if that proton was going towards the ceiling and the magnetic field was towards Canada and down 70 degrees, what's the angle between my arms? Well, that's 90, that's 70, that's a total of 160. What if that particle was going south and level with the floor? Okay, and the magnetic field's like that. What's the angle between my arms? Well, that's 90, and that's 20. That's 110. Every problem's different. But if you've got those different colored pens and you put them in the direction of the velocity of the magnetic field, you're golden. Oh, because the particle's going east and the magnetic field is going north and down. And if you look at my arms here, that's 90 degrees. Okay? Now, if I plug in those values, there's the elementary charge, there's the speed, there's the magnetic field. What I get is a number that no one cares about, 4 times 10 to the minus 17. Now, some of you are saying, Greg, that's 10 to the minus 17 newtons. That's negligible. That's teeny tiny. But that force is pushing on a proton with a mass of 10 to the minus 27. 1.67 times 10 to the minus 27. That's going to cause a huge, enormous acceleration. That's not a negligible force to a proton, okay? Now, here's where right-hand rule number 1 comes in. What direction is the force on that proton? Okay. Well, we first of all reach in the direction of the motion, and then we turn our wrist so that we can wave in the direction of the B field. That's Canada and down. And my thumb is pointing in the direction of the force for a proton, which is what we've got. If it were an electron, I'd reverse that. Okay, but it's a proton, and so the force is like that. Check on your neighbor, please.
I was also on one. Wait, no, it's just.
What's that?
The direct.
Yes, exactly the opposite direction. Just take whatever you get with the right-hand rule, go the other way.
Mines are under. During a lot of them.
Yeah, it's sometimes.
Right, the other.
Oh, the motion of the proton is the flow, is the most, it's the velocity. And so I reach in the direction of that, and then yeah. And then turn your wrist so that you can wave in the B field. Oh, when we talk about current, it's always the flow of positive charge. So
Yeah.
what's that? Yeah, this is just one single proton. We're not talking about a current. Yeah. Okay. Again, I promise you, you will have a problem like that on the exam. A problem like that. So this is right-hand rule number 2. And again, it's not physics. It's a memory device. There's 2 ways to make a circle around a straight wire, and I just need to remember which way it goes. And so I use my right hand. Now, some of you are feeling hard done by. You're saying, well, I just happen to be left-handed, and you're doing everything for the right-handers, and I'm being left out. Oh, no. The left-handed people have the advantage because you can keep taking the exam while you figure out the problem. Okay? The right-handed people have to put down their pen and figure out the problem. Okay? Again, if you're left-handed, you are more likely to become a scientist. You're also more likely to go to prison. So you got to choose one way or the other. That's just statistics. That's just statistics. Okay? Now, in the tutorial, we dealt with a current loop. And this is a very, very common situation in the world that we live in. Often we have current going in loops. And we started with a square loop so that we could consider it as 4 straight wires. 1, 2, 3, 4. And what we're going to do is we're going to use the second right-hand rule to figure out the direction of the magnetic field for each of these straight wires. Well, let's start with the top wire. And right here, the current's going to the right. And so that means that above the current, it's going to be into the board, into the screen, and below it's going to be out of the screen. Does everyone see how I got that? If I look at this here, if I let my thumb be the current, above it's going away from you, and below it's coming towards you, my fingers. Away on the top and towards on the bottom. Now, if that current, conventional current's going to the left on top, it's going down on that side. And that means that the magnetic field's going to be away from you over there and towards you in the middle. On the bottom, it's going to your right. And that means it's going to be going away from you on the bottom and towards you in the middle. And then on the side, it's going to be going away from you on the outside and towards you on the inside. Now, what does that look like? that looks like a whole lot of magnetic field lines coming towards you through this wire and then wrapping around and coming back around. Okay? But they're coming towards you. Now, what I'm going to do is I'm going to turn that, I'm going to rotate that, and I'm going to rotate it like this. Okay? So, see how the current was going to the right? To the right? Well, now I'm going to rotate it so that it's coming out towards you. Now, wait a minute, Greg. What is that? What is that? This is a representation of a loop. What we've done is we've taken a loop, okay, and we have removed the front half of that loop and only show the back half of that loop. And that current is going away from you at the bottom, up the back, and out at the top. And that's the representation that we use to make it clear which way the current's going. Does everyone see what's going on there? Okay. I love it. I love this demo. I like that. Okay. Now, let's think about what those field lines look like. They were all coming out towards you in the middle. And then I rotated it like that. And so now they're all going to go to your right. And they're going to go to the left outside. And in the middle, they're going to go to the right. Now, we have seen this magnetic field before. It's a magnetic field due to a short bar magnet. And that's a beautiful thing. Because current loops are hard. Current loops are messy. Until you replace that current loop with a short little bar magnet, and then it becomes a second grade problem. We've known how to deal with little bar magnets since the second grade. We played with them, okay? So once you take that current loop and replace it with a bar magnet, easy peasy. Now, what that means is that every current loop has a north side and a south side. Well, how do I remember which side is the north side, Greg? Your right hand, okay? You take your right hand, and part of your right hand is curved, and the loop is curved. So you use the curved part of your right hand to represent the current going around in the loop. Your thumb is now pointing to the side of that loop that's the North Pole. Or you could say your thumb is directed in the your thumb is pointing in the direction that the magnetic field lines pass through the loop. Okay? So that's what we do is we use our right hand rule. We call that right hand rule number 3. And again, it's just a memory device. I have a hard time remembering which side of the loop is the North Pole. I use my right hand. Check that your neighbor has all 3 right hand rules down. All 3 right hand rules.
All seems like the same rule. One is the
Cream. They make the best.
second wire.
Okay. Questions?
We'll go in the direction of the one side. I just think of it like it's finding B.
Oh,
The first one is to find those.
if I look at the magnetic field due to a loop, they come out one side of the loop, they wrap around and go into the other side of the loop, and that looks like a bar magnet. Okay, so whenever we have a loop, we just think of that as a bar magnet, and it makes the problem so much easier. So much easier. Now, last day in the video, there was this demo where I made a Pepsi cup into a speaker. Now, this morning, this dropped on the floor, and it sometimes works and it sometimes doesn't. we're gonna see if we can make it work. Come on. Whenever current's going out to the speaker, and remember there's a coil in the back here. You see if you can see it. There's a coil back there, and that's going to act like a little magnet when there's current going through it. And there's current going through it when I'm supposed to have sound. And that current will also go through this bulb and make it light. This morning it just started lighting itself. So when it lights, just flag me down and we'll do the demo. Okay. Now, sometimes it works. So which side is north for that loop there? Which side is north? Tell your neighbor real quick. Okay. How many say that way? How many say that way? How many aren't sure? Yeah, that's pretty confusing. And that's why we use this representation here. Because this representation, it's not confusing. It goes in at the bottom, it comes out of the top, and that means that the north is right. That's why we use the donut method. Okay?
That way it's still going the same way.
Now,
That's what I thought.
the Earth, we said, has a magnetic field that looks a whole lot like a bar magnet. But the north magnetic pole is down in the south where the penguins live. And the south magnetic pole is up where Canada is. Okay? And that's confusing. But that's the way it has to be, because the South Pole up in Canada is what attracts the North Pole of our compass, right? Now, we believe, we don't fully understand it, but we believe that this is caused by a flow of charged material, melted magma, some sort of, I don't know, I don't understand it, but something's flowing around the equator that has charge. And the question is, what direction would conventional current have to flow around the equator to make this kind of a magnetic field? Would it have to go from east to west or west to east? Would it go from Boston to California or from California to Boston? Talk to your neighbor. Oh, it lit up. Why didn't you tell me? You have one job. Alice, you have one job. Okay. Again, point your thumb in the direction of the North Pole. Is that music?
Yes.
Oh, and then it went away again. I know a pity clap when I hear one. Okay, so the current has to go from east to west, from Boston to California, okay, in order to give me that North Pole down.
The bigger one.
Okay, now, more common than a single loop is multiple loops, lots of loops, and we call that a solenoid. And if we use superposition, what we find is that if a single loop acts like a short bar magnet, a lot of loops, a solenoid, acts like a long bar magnet. Okay? Now I have a demo for that. I have here a solenoid, and I sprinkled some iron filings on this piece of glass here, and then I'm going to pass current, a lot of current, through that solenoid, and hopefully we will see those iron filings move. you saw the ones in the middle go straight, right? I'm just tapping it to let them jiggle to their happy place. I can only do that when the light's on. It tries to keep itself from overheating. Is it starting to look like the magnetic field due to a bar magnet? You see they come in at this side, they come out at that side, and they wrap around. And then they go straight there in the middle. Okay, and so they look like that. Okay, let's turn this off, hey? Yeah. Now, this begs the question, why does a solenoid act like a bar magnet? And that's the wrong question. The right question is, why does a bar magnet act like a solenoid? That's the right question. And let me suggest a possible answer. This is a model, but if we were to model each atom of iron as a current loop, okay? That's the first assumption we're going to make. And then if we assume that all of those current loops are rotating in the same direction, in this case, if we're looking down on this, they're all going clockwise, okay? And we'll talk about why they're all lined up in a minute. But let's just suppose that they are. They're all lined up. Now, if I look anywhere inside, like let's say I look right here. Well, this current loop is going down. This current loop's going up. That's going to cancel. If I look down here, this current loop's going to the left. This one's going to the right. That's going to cancel. If I look right here, this one's going down and to the left. This one's going down and to the right. This one's going up and to the right. This one's going up and to the left. That's going to cancel. Everywhere inside, it cancels. Where it doesn't cancel is on the side. There's nothing to cancel with. And so it looks like I've got current there. And 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 there. Okay? Along the outside, it looks like there's a continuous current. Now, there's no charge that actually goes around the outside. This little charge just goes from here to here. But it looks like I've got a continuous flow of charge all the way around the outside. We call that magnetization current. Okay, magnetization current. So a magnetized piece of iron looks like a solenoid. Looks like there's current around the outside.
What about in the middle of the little?
Oh, we assume that we're modeling that that atom as having a net charge that's going around in a circle like this. So in the middle, we just have the nucleus of the atom, and that's not making a current loop. Okay. Now it's more complicated than that. It's much more complicated than that, but this is what's going to get us to Zion. Okay. Now, the question is, how do we get those lined up in the first place? How do we get them all lined up? Well, a loop produces a magnetic field that looks like it's a magnet. And the question is, does a loop react to an external field like a magnet? And the answer is, well, yes. If it looks like a magnet, it acts like a magnet. Okay? So if I have a magnetic field that's pointing towards that open door, and I put a current loop in there, the first thing you want to do mentally is replace that current loop with a bar magnet. Okay? And so the current going in at the top, down the back, out the bottom, and that gives me a magnetic field with the north up, the north up here. Now, a bar magnet that's free to rotate, it's a compass needle, okay? And that compass needle is going to line up with the magnetic field that it finds itself in. How? Like that. Now, if all of those atoms, those iron atoms, look like little compass needles, and I can put them in a strong magnetic field, they'll all line up. So what I'm going to do is I'm going to take this bar of iron, and it's not a magnet. It's not picking up any of these paper clips. But if I put it in a strong magnetic field, and I just whack on it a little bit to jiggle the atoms, I can make it into a strong magnet. Okay, I can magnetize it. Now, how do I unmagnetize it? Well, can I move this for a second? Anyone that has been in charge of a science lab knows the answer to this. You just drop them, okay? And over time, if you just keep dropping them, that causes them to just kind of get randomized again so that they're not lined up. And eventually, it just stops being a magnet. Now, this is still a magnet. This is not soft enough iron that I could demagnetize it with just that many drops. So I'd have to really whack it on the floor, and I don't want to do that. So another way to demagnetize it is with an AC current source and a solenoid. Now remember, AC stands for alternating current. This source changes the direction of the current 120 times a second. Sometimes going this way, then going that way, then this way. And that changes the direction of the magnetic field in the solenoid back and forth 120 times a second. So if I turn that current on and I pass this iron through there, lo and behold, it's demagnetized. Okay. Now I can magnetize it using that same solenoid. But instead of an AC source, I'm going to use a DC, direct current source, where the current's always going the same direction and the magnetic field is always pointing the same direction. So let's do that. Let's take these leads and plug them in over here. And I turn this on, and now I pass that through. And lo and behold, it's a strong magnet again. Now, another way to demagnetize this is to heat it up. You know, when you heat things up, you're introducing random motion to the molecules. And if you get enough of that thermal energy into your molecules, you can actually break that connection between neighboring dipoles, and you can get them all jumbled up again. You have to raise the temperature above what's called the Curie temperature. And that Curie temperature is different for different materials. But that's another way to demagnetize something. There's a third way to magnetize a iron rod, but it's not very effective. If you line up the rod with the Earth's magnetic field, which is towards Canada and down 70 degrees, and then you just whack it for all you're worth. You just wail on that puppy. You can get a small magnetic field. But if you're lost in the wilderness and you need a compass, that's all you got. Okay, you got to line it up. Well, if you don't have a compass, you don't know where Canada is. Never mind. You're lost. Okay, you are lost. Okay, now we magnetize the rod. How many of you are feeling like we've learned too much? Yeah, okay, yeah, that group right there. The slow group. Oh, you got a question. I thought he was just telling me that his neighbor's lost.
You change the pole of the magnet by putting it through a hole.
Oh, yes, you can. You know, and if you remember, if you watch that video that I left you, when we did the Ørsted experiment, 3 of the compasses were pointing in the right direction, and one of them was pointing the opposite way. It had gotten magnetized the opposite way, and so if you're in charge of a lab, you got to check all of your magnets before the lab starts to make sure they're still, the north is still the north. Okay. Now, I would like to point out that even though it looks like there's a whole lot to remember, there's not that much. And I'm going to try to put it all together right now. We're going to put it all together. We're going to find that there's 3 ways to set up a magnetic field. Only 3 ways. Okay, it's not like we're asking you to learn all 12 bones in the body. Okay, just 3. So let's talk about those 3. The first is with a bar magnet. And we know that the magnetic field comes out of the north, wraps around, and goes into the south. And we learned that with our compass. Okay. Now, most of the time, we deal with the magnetic field right next to the North Pole or the South Pole. Right next to the North Pole, we take that magnetic field to be away from the north, and near the South Pole, we take it to be towards the south. That's simple. Now, the second way is with a solenoid. And I'm going to need a bunch of donuts here. And if I want the North Pole to be here and the South Pole to be there, by right-hand rule number 3, I need these to be out of the page and these to be into the page. Now, what we find is that the magnetic field comes out of the north, wraps around, and goes into the south, just like with the bar magnet. But here's the new stuff. Those magnetic field lines close on themselves. So outside of the solenoid, they go from north to south, and inside the solenoid, they go from south to north. Okay? So out of the north, wrap around into the south, and they keep going. Now, what that tells me, since a bar magnet acts like a solenoid, is that outside of the bar magnet, where I can put a compass, they go from north to south. But inside the bar, where I can't put a compass, where it's dark, they go from south to north to complete the loop. Okay? And here I used right-hand rule number 3. Now, the third way is if I have a long straight wire carrying conventional current. And remember, what you're looking at there is this wire with current coming towards you. And we know that the magnetic field due to that wire is concentric circles. And by using right-hand rule number 2, I can tell which way those circles go. And so if I wanted the magnetic field at any location, like here, it would be tangent to those circles. And this is by right-hand rule number 2. Okay? Those are the 3 ways to create a magnetic field. And remember, it's always a 2-step dance. Something creates the magnetic field, and then the magnetic field pushes on something else. Well, how do we push on something else? Well, there's 4 ways. Let's look at those 4 ways. The first way is if I have a single charge, let's make it a positive charge, that's traveling in some direction with some velocity. in a magnetic field that's represented by the blue lines. Well, the magnetic force is given by the Lorentz force equation, where this is theta, the angle between velocity and B, and the direction is given by right-hand rule number 1. Okay, so I reach in the direction of the motion, I turn my wrist so that I can wave in the direction of the B field, and that gives me the force into the page. Now again, if you can draw the velocity vector and the magnetic field vector on a flat piece of paper or a flat screen, there's only 2 possible directions for that force, either out of the screen or into the screen. It's got to be perpendicular to the screen, because the magnetic force is always perpendicular to those 2 vectors, the velocity and the magnetic field. Now, the second way is if I have a wire that's carrying current, and if that wire is length L and it's in a magnetic field, then the force is proportional to the current and the B field and the sine of the angle between them, and that's the force per unit length. And you will never use that formula, not in your homework, not on the exam. But you will need to know the direction of the force on a current carrying wire. And that direction is given by right-hand rule number 1. You reach in the direction of the flow, put your wrist in the direction of the B field, and that gives me a force into the page. But it's all along the wire. The whole wire is pushed into the page. Now, the last 2 are forces on bar magnets, okay? And the first case we're familiar with, if we have a uniform magnetic field, and we put a bar magnet in there, I can think of that bar magnet as a compass needle, where the North Pole is the arrowhead on the compass needle. Now, this is not a real scientific explanation, but it works. It gives correct answers. If you think of the North Pole of a bar magnet being pushed in the direction of the magnetic field and the South Pole being pushed in the opposite direction, much like what we had with the electric force, you get the right answers. And because this is a uniform magnetic field, these forces are equal to each other, meaning there's no net force on that bar magnet, but there is a net torque. And so this bar magnet's going to rotate until it lines up with the magnetic field. And we've seen that over and over again. That's just a compass needle lining up, okay? Compass needle lining up. Now, this last one is new, but not really. This is something you've known since the 2nd grade. If your magnetic field is not uniform, if it's strong in one region and weak in another region, the field lines close together here, far apart there, that would be the case, say, next to a great big South Pole. Well, if I put a bar magnet in there, 2 things happen. First of all, that bar magnet's the North Pole's going to feel a force that way, the South Pole's going to feel a force that way. This thing is going to whip around and line up. Much like this. But here's where it's different. The North Pole is now in a strong magnetic field, so it feels a big force. And the South Pole's in a weak magnetic field, so it feels a small force. And so this thing is going to be sucked over to the right. Now, I said you understood that since the second grade. Well, if you put a strong South Pole here and glue it to the table, and then you just set down a bar magnet here, the first thing that's going to happen is it's going to whip around so the north is towards the south, and then it's going to slide across the table to meet the South Pole. Does that make sense? Now, let me show you that in action here. My bar, it's here, okay? I have here a solenoid and a DC power supply. This is going to act like that South Pole over there, giving me a magnetic field that's non-uniform. It's strong near the pole and then weak out here. And watch what happens when I turn on the current. Did you see that? Okay. Do it again. Okay. Just sucks right in. Okay. Now, years ago at University of Washington, we had a huge solenoid, big old huge solenoid. And in our table, our demo table, we had 10 car batteries hooked in series, 120 volts DC. It was deadly, okay? And we got this current going in this huge solenoid, and we had a great big old metal iron core. And we would put it next to the solenoid, and it would suck it right in, and then it would just kind of wobble in the middle. Well, it didn't take long for us to figure out that we could close the switch and get this thing racing towards the center, and then we'd open the switch when it got to the center, and it would race out the other side, and this was a rail gun. And we could get it going down the hall until we got in trouble for that, okay? Now, why would we want to use this? Well, we would want to use this to protect our children, okay? Someday, not today for you, but someday soon, you're going to have to buy a car for your children. And you don't want 75 amps anywhere near your child, okay? Now, in order to get your starting motor to turn your engine over, you are going to need 75 amps going through that starting motor. And if you're using the key to close the switch, that means 75 amps are going through that steering wheel column next to your child. That's not a good thing. Now, you know that whenever you buy a starter, whenever it goes out and you replace it, there's a little tube on top. Well, that tube is a solenoid. It's just this with a plunger that is just like that bar, okay? Now, this is what happens. When I close the switch at the ignition, that causes a little bit of current, like half an amp, to go through that solenoid that sits on top of your starting motor. That pulls an iron rod down, like we saw, and that closes the real switch, that closes the switch for the starter motor that gives you the 75 amps. That way the 75 amps are nowhere close to your child. Does that make sense? Okay. Now, don't quote me, but I've had a lot of starter motors go out. And what I find is that if I just get out of the car and take anything that's really heavy and just wail on the top of that starting motor, actually wail on the solenoid, usually the solenoid is just stuck, it's gummed up or something, and if you could just hit it hard enough, it'll free it up and it'll work for another day. Okay, and eventually you're getting out every time you start the car, and it looks really funny at church. Okay. Okay, let's use our clicker. let's say that this current loop is stapled to the sky. It's kept in place. It's fixed in place. And we want to know the direction of the force acting on this other current loop on your right. And these are your choices. Is it to the left, to the right, up, down, or no net force? And I'm going to get you started here. Bear with me.
Like, it's this way.
Okay, now you can click.
What you need, bro? You need like 30 seconds. As well.
Next week, next week.
You people look like you're trying to swap mosquitoes.
Second is on a little right side.
Last call, get your vote in.
Also wasn't.
Okay, is that everybody? Maybe not. Whoa, okay. We're not there. We're not ready. Remember what I said. This goes in your toolbox. Loops are hard until you replace them with bar magnets. So let's replace them with bar magnets. By right-hand rule number 3, the right-hand rule gives me the north on the right for that one. If I do the same thing for this one, I get the south on the left. And now you go back to the 2nd grade and ask yourself, if I put those 2 bar magnets down on the table, what's that south going to do with that north next to it? It's going to be attracted. It's that easy. Okay, it's that easy. The force is to the left. Okay? Folks, that's as far as the morning class got, so let's stop there. A blessing on your heads. Yeah.